All right, let's go ahead and talk about intermolecular forces. And so intermolecular forces are the force of attraction that occurs between molecules. And so molecules can have different types of attractive forces, and we're going to go through and talk about some of those different types of attractive forces. But before we get started, let's go ahead and think about these green BBs here. And so we're going to pretend these are molecules, all right? So think about the molecules here. And so if you take a look, they're kind of not really attracted to each other. I mean, they are stuck in the cup, but they easily separate from each other. And so we can say that there's not a lot of attraction between these green BBs. See, if you go like this, there's not a lot of attraction. So there's little intermolecular forces. On the other side, though, think about these. All right, and I've used this as a lot. I've used these for a lot of examples here. But if you take a look, we're going to pretend each one of these is a molecule. Now, if you look, they are really stuck together. They kind of are hard to pull apart, and you can pull it apart, right? So you can pull it apart, but there's a strong attraction between these molecules, all right? And so the intermolecular forces of these molecules are very low. The intermolecular forces of these molecules are very high. And so what we're going to do is we're going to talk about those force of attraction that occurs between molecules and how we can determine if a molecule has strong intermolecular forces or if it has little intermolecular forces. So in the liquid and solid states, molecules are held together by intermolecular forces. And there are several types of intermolecular forces that vary in strength depending on the dipoles involved. And so we talked about dipoles. Dipoles occur when you have a polar bond, right? The bond itself will have a dipole where you have a partial positive and partial negative end. We've also talked about polar molecules, and so molecules themselves can have a partial positive and partial negative end. And depending on how strong the dipole is, depends on how strong the intermolecular forces are. So what we're going to do is we're going to go through 4 types of intermolecular forces, and we're starting with the weakest one, and we're going to go to the strongest one. And so a specific type of weak dipole-dipole force is called London dispersion forces. And those are a result of electrons which are orbiting the nucleus instantaneously all going on the same side of an atom, to where you get a partial positive end and a partial negative end within the atom itself. And what ends up happening is because you've got this instantaneous dipole, there's a force of attraction between 2 different atoms that's occurring with. So let's go ahead and take a look at these atoms. So if you look at the London dispersion force, look at the atom on the left there, on the top on the left, the first example. Notice how the electrons are evenly distributed. But again, they're going around the nucleus of the atom, and kind of like the planets going around the sun, you can actually have a situation where all of the planets are on the same side of the sun. Now, that's very rare, but you can have a situation where all the planets are on the same side of the sun. You can have the same situation with electrons. You can have it where all of the electrons instantaneously occur on the same side of the atom. And notice how in the second picture, the picture on the right, notice how when all of the electrons are on that side, it creates a partial negative on that side and the partial positive. Now what happens is, if you look at the second set of pictures, if you have this occurring in one atom, it will occur also in another atom, and there will be a sort of force of attraction between them. And so the partial positive of one atom is going to be attracted to the partial negative of another. Now this is temporary, all right, but typically when the electrons move back to normal distribution of one atom, it'll also occur in another, the other atom as well. And so it kind of, they do sort of move around in unison with each other. All right, so this does occur in all atoms, because all atoms have electrons, and so you can have it to where all the electrons are on one side of an atom again, and again, because all atoms have electrons, this occurs in all atoms. So think about the electrons that are in these two molecules. All right, so both of these molecules here have electrons, and you can have a situation where all the electrons end up on one side of the molecule. All right, something that affects London dispersion force is surface area. And so if you have a molecule with a lot of surface area, that's a lot of exposure to having that dipole-dipole interaction. And so here's an example of what I'm talking about. If you look at particularly the picture on the right, notice the red lines. The very, very right molecule and the molecule that's right next to it, they actually have the same chemical formula, but the atoms are oriented in a different way. So they have the same chemical formula. Notice how they have the same molar mass. So they have the same number of carbon atoms and the same number of hydrogen atoms. However, the one on the far right, look at the boiling point of the one on the far right. The one on the far right is 36.1 degrees Celsius. Notice the second, the one that's right next to it is 9.5 degrees Celsius. So the one on the far right has a high boiling point. And the reason why that is, we're going to talk about this in a moment, is the stronger the force of attraction, the higher the boiling point. And so think about this boiling. Boiling is where, again, you go from liquid to gas, right? And the molecules are separating from each other. And so if you think of these molecules here separating from each other, it'll be very easy for them to separate from each other. However, think about these molecules separating from each other. They don't really want to separate from each other, so it's going to take a lot more energy for that to occur. All right, now, so the first intermolecular force was London dispersion force. The second type we're going to talk about is dipole-dipole forces. Now, dipole-dipole forces essentially is if you have a polar molecule, that molecule has a partial positive and a partial negative end. So the molecule itself has a partial positive and a partial negative. And notice how in the first diagram, notice how the partial positives and the partial negatives are attracted to each other, kind of like these are attracted to each other. And so there's a force of attraction that occurs, and so what happens is it makes them want to stick together more. And so that is dipole-dipole interaction there. The next type of intermolecular force that we're going to talk about, it's another type of dipole-dipole interaction. However, it's a special type of dipole-dipole. It is called hydrogen bonding. Hydrogen bonding is a type of dipole-dipole, but it's an extreme type of that. So it's a very strong type of dipole-dipole interaction. Essentially, if hydrogen is covalently bonded to fluorine, oxygen, or nitrogen, you will have hydrogen bonding. And what happens is those three atoms, and if you take a look, they're the three that are right here, fluorine, oxygen, and nitrogen. If hydrogen is bonded with these three, it creates such a large very polar bond, so the bond is extremely polar, that you're not just going to have like a partial negative, you're going to have a very large partial negative and a very large partial positive. And so what ends up happening is, because they're very, very large partial positives and negatives, the force of attraction with other molecules that have these partial positives and negatives is going to be very strong. And so if you take a look, water is a great example of hydrogen bonding. So notice how H2O, that's water, and the hydrogens are covalently bonded with the oxygen, but the hydrogen bond is actually the attraction of one hydrogen with a different water molecule's oxygen. And so notice how, again, it's similar to dipole-dipoles. It's exactly like dipole-dipole, the same concept, kind of like this here, where you have the partial positive, partial negative attracted to each other, but it is a much stronger force of attraction. And this is actually the reason why water has the properties that it has. It's able to stick to many surfaces. It has very strong surface tension, which means it's hard to break the surface tension, and it's able to dissolve a lot. And so the hydrogen bond itself is the dotted line. And so if you're looking at that diagram, the dotted line is the hydrogen bond. What I want to say though is the hydrogen bond is not the covalent bond. So something very important, again, the hydrogen bond is the dotted line. And it is not an actual bond, but rather a very strong force of attraction. So I really want to highlight that. Now, this is the strongest dipole-dipole interaction that we've talked about, but the other thing that I want to say is that hydrogen bonding is not as strong as covalent bonding. And so covalent bonds are very strong bonds, and this is just a strong type of intermolecular force. All right, so this is a really great example of hydrogen bonding and dipole-dipole interaction. So notice these molecules here. Notice how there's the carbon is partially positive, the hydrogen is partially positive, and the oxygen is partially negative. Notice the red dots between the oxygen and the carbon. That's dipole-dipole interaction. The partial negative of the oxygen is attracted to the partial positive of the carbon. But then look at the hydrogen bond. The oxygen is attracted to the hydrogen of the other one. The hydrogen bond is a stronger type of dipole-dipole, so the force of attraction with the hydrogen bond is going to be greater than the force of attraction with the dipole-dipole. What I will say is this type of molecule will have a higher melting point and a higher boiling point than other types of molecules because this has several types of intermolecular forces. All right, and the last one that we're going to talk about is the strongest intermolecular force, and that's dipole-ion. And so again, dipole-dipole is between partial positives and partial negatives, but an ion is a full positive and a full negative. And so dipole-ion is the force of attraction between molecules that are polar and an ion. And what ends up happening is because the ions are full positives and full negatives, kind of like this example here, notice the sodium ion is a full positive. What ends up happening is it's actually able to attract a lot of partial negative ends of different molecules. And so it's able to attract many different molecules. Same thing with the negative anion there. Notice how it's attracting a lot of different dipole, or a lot of different molecules that have a dipole. So now physical properties such as boiling point, melting point, vapor pressure, surface tension, they're all affected by the strength of the intermolecular force. So the stronger the intermolecular force, this is what you want to think. The stronger the intermolecular force, the more the molecules want to stick with each other. So let's go ahead and review a couple things about states of matter. This is a solid, and notice how if you make things colder, notice what happens to the motion of the particles. The motion of the particles slow down. If you heat it up, notice what happens to the motion of the particles. The motion of the particles go faster. And so we're going to learn this later in the year, but temperature is a measure of the kinetic energy. It's a measure of the motion of the particles. And so the hotter something is, the more it'll move, the more it'll vibrate. And so that's something we want to keep in mind, that as we increase the temperature, the particles are moving more. And to go from a solid to a liquid, the particles have to be moving enough to separate from each other. And then to go from a liquid to a gas, it's the same thing. They have to be moving enough to separate from each other. And so we want to think about this in terms of boiling point, melting point, in terms of intermolecular forces. And what we're about to talk about is the greater the intermolecular force, the higher the boiling point. It's because the greater the intermolecular force, the more the molecules want to stick together. So let's go ahead and really talk about these physical properties and how they're affected. So the strength of the intermolecular force will affect the boiling point, melting point, vapor pressure, and so on. So let's go and talk about vapor pressure. One of the many ways to determine the strength of intermolecular force is to measure the vapor pressure. And what vapor pressure is if you take like a cup of water and you leave it out and you leave it there for a week, eventually the water will evaporate and there'll be no more water. And that's what the image on the left is kind of showing. But imagine you take that cup of water and you close it and you make a closed container. Well, what will end up happening is it will evaporate, but notice how some of the molecules are evaporating, and then notice how some of the arrows are showing the molecules going back into the water, or going back into liquid, not the water, the liquid. So some of the water molecules are becoming a gas, and some of the gas particles are becoming liquid. So it's going between gas and liquid. So there's a point at which equilibrium is achieved, and we haven't really talked about equilibrium. We'll talk about that a lot more next semester. But essentially, what equilibrium is, the amount of molecules becoming gas is equal to the amount of molecules becoming a liquid, and so it's an equal amount. So it's not that you have the same amount of each, it's just the amount that's becoming gas is equal to the amount becoming a liquid. And so in a closed container, once the rate of vaporization and condensation are constant, the total amount of vapor won't change. So there are vapor molecules becoming a liquid, and there's liquid molecules becoming a vapor, but it's the overall amount will not change. And this is called dynamic equilibrium. What I'll say is we don't really need to understand dynamic equilibrium at this particular moment for this unit. We will talk more about it in the future. But essentially what happens is, again, the amount becoming gas is equal to the amount becoming a liquid. But when this occurs, it's going to create a certain pressure. And so take a look at this. So it's going to create a certain pressure, and the pressure that it creates is dependent on the intermolecular forces. And so let's think about this. Let's think about if I were to want to turn this into a liquid here, right? Or I'm sorry, gas. So let's say this is a liquid, and let's say I want to turn it into a gas. Well, if I add some motion to it, notice how they're starting to fly off. And so I can sit there and I can add enough, and they start to fly all over the place. And now I have to clean that all up. But imagine doing that with this. Imagine doing that with this. If you were to sit there and you shake it all you want, you can shake it really, really hard. It's sticking together more compared to this, because this has a larger intermolecular force. This has small intermolecular forces. And so small intermolecular forces means that it will vaporize more easily. And so if it's able to vaporize more easily, that means that you're going to have a higher vapor pressure, because you're going to have more molecules in the vapor state. And so the pressure exerted by the vapor when it is in dynamic equilibrium is called the vapor pressure. The weaker the attractive force is, the more molecules will be in the vapor phase. That means that the weaker the attractive force is, the higher the vapor pressure. So weak attractive force, that means they're not attracted to each other. That means they're going to be in the vapor phase. Means high vapor pressure. Now, boiling point, same concept, but it's opposite. So the stronger the intermolecular forces, the higher the boiling point. So think about what boiling point is. Again, boiling point is going from liquid to gas. The stronger the force of attraction, the higher, the larger amount of energy needed to separate the molecules. And so you will need a higher temperature. So if there's a strong intermolecular force like this, it would require a large amount of heat energy to separate those particular molecules. So the stronger attractive forces, higher the boiling point. Also, the higher the melting point. And that's it. So really it comes down to how strongly the molecules are attracted to each other. If there's a very strong force of attraction, that means they're going to have a higher boiling point. They're going to have a lower vapor pressure, because if there's a strong force of attraction, there's not going to be a lot of them in the vapor phase. So that is kind of the sum of intermolecular forces. So we did go over the four. Make sure you review real quick the chart that's in your book that kind of lists them. All molecules have London dispersion. Polar molecules have London dispersion and dipole-dipole. Something that has hydrogen bonding, which is hydrogen bonded with NO or F, is going to have hydrogen bond, which is a type of dipole-dipole. And then we have dipole ion, which occurs between polar molecules and ions. And we'll do the guided practice problems in class. Hope you guys have a great great break, and I will see you guys in class.